The periodic table. So 1869, Mendeleev, he was a Russian scientist. He noticed that certain groups of elements had similar properties. At this point in time, a lot of elements had been discovered, but there was no periodic table. It was just, people had this information about these different elements, and there wasn't any order to it. So he was looking for some pattern, some way to arrange this that would make it more useful. And he found that if he listed the elements in order of increasing mass, that those similar properties reoccurred in a periodic pattern. Periodic just means to exhibit a repeating pattern. So this is an example of that. So if you take the first 20 elements and you line them up by increasing mass, the colors here, pink, 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 that indicates that those elements have some properties in common. And here's a green, and later green and green. Those have some properties in common. Those similar properties recur periodically. It's a little bit like the keys on a piano keyboard. You've got 2 blacks and 3 blacks, and 2 blacks and 3 blacks. And those, if you press the C sharp key, there's multiple C sharps, and the difference is just that they get higher and higher as you go up, but they have something in common. So when the elements are arranged in order of increasing mass, certain sets of properties recur periodically. That's what's known as the periodic law, and Mendeleev is credited with that. So he took the elements that were known at the time and he arranged them in a table so that the elements with common properties ended up in rows. So lithium, sodium, potassium are columns. In a column together. Beryllium, magnesium, and calcium are in a column. Helium, neon, argon, they have similar properties. And it 1 through 8, and then it repeated. And so he then called that was called a periodic table. There were some gaps in this table because he was lining them up by properties, and there were some holes. And he predicted that elements would later be discovered to fill in those holes. And his predictions were very correct. He even predicted things like melting point, density, color, and how they reacted with other elements. And he was very accurate in his predictions. He predicted the existence of an element he called ecosilicon, an element below silicon on the table, and that was discovered in 1886. It was named germanium after Clemens Winkler's home country of Germany. And this is how, in 1869, Dmitri Mendeleev completed the first periodic table. Tetris, anyone? Yeah. My feeble attempts at humor. In the modern periodic table, the elements are listed in order of increasing atomic number rather than increasing relative mass. Back in 1869, Mendeleev didn't know about protons, so he was going by atomic mass. If you look, there's a couple of places where they are out of order in terms of mass. Let's see if we can find them. Anybody see one? Tellurium and iodine. So 52 and 53. We would expect 53 to have a larger mass, and its mass is smaller. It's 126.9. Tellurium with 52 protons is 127.6. And the reason for that has to do with the number of neutrons. So the ordering principle is really the number of protons and not the mass. We also have a lot more elements in our periodic table because many more have been discovered. And then in addition to the naturally occurring ones, some have been synthesized. And in fact, just at the end of December, they announced names for another 4 elements. So that's pretty cool. There are some divisions in the periodic table, and we need to be aware of these. This table has been color-coded. All of these yellow elements are metals. The pink ones are metalloids, and the green ones are nonmetals. There is a stair-step line that divides the nonmetals from the metals. And you can see it on this periodic table as well. So you need to know that everything to the left of that, all of these guys are going to be a metal. The ones right adjacent to it, they're touching. Those are the semi-metals or the metalloids, except for aluminum. And hopefully we can all remember that aluminum is a metal. Think about the pans in your kitchen. It's definitely a metal. And these guys are nonmetals. So we can classify elements as being metals, nonmetals, or metalloids. I'm going to go over this real quickly because you should be able to just read this from your textbook. Metals are good conductors of heat and electricity in general. They can be pounded into flat sheets, that's called malleability. They can be drawn into wires, it's called ductility. They're often shiny. And one of the most important things for chemistry is they tend to lose electrons when they undergo chemical changes. So if a metal atom loses electrons, is it going to be a cation or an anion? It'll be a cation because it started out with an equal number of negative and positive electrons and protons. If it loses electrons, then overall it's going to have a positive charge. The nonmetals, their properties vary a lot more than the metals do. 5 of them are solids at room temperature, 1's a liquid, and 11 are gases. So they're just kind of all mixed up together. Of the metals, they're all solids except for mercury. On this periodic table on the wall, if the element symbol is blue, that means it's a liquid at room temperature. If it's black, it's a solid, and if it's red, it's a gas. So that can be helpful. Nonmetals tend to be poor conductors of heat and electricity. They're generally not ductile or malleable. They tend to be brittle. And what's most important for chemistry is they tend to gain electrons. So when they gain electrons, are they going to make cations or anions? Anions. So nonmetals tend to form negative ions, anions. Metalloids are sometimes called semi-metals. This always makes me think of humanoid robots. So a humanoid robot like C-3PO, right? He kind of looks human, right? He's got a torso and a head and arms and legs, and he walks and moves a lot like a human. But is he human? No, he's just kind of like a human. Well, the metalloids are like the metals in some respects, and in other ways they're not. And so it seems reasonable that they're between the metals and the nonmetals in the periodic table. Their properties are between. They are very useful. You've probably heard of semiconductors. And here in the Central Valley, we're not too far from the Silicon Valley, right? Lots of computer industries there. Silicon is a very important semi-metal. It's a semiconductor. Their properties of electrical conduction can be controlled by things that we do to them. They're temperature sensitive, and we can dope them with various things, and we can control their conductivity. So that makes them very useful in electronic devices. Other divisions in the periodic table, main group versus transition elements. The main group elements tend to be very predictable in their properties. The transition elements are much less predictable. I think of them as being squirrely. They're just kind of unpredictable. Here, the groups that stick up, these are the main group elements. So these columns, the first 2 columns and the last 6. The ones in the middle, where it looks like the periodic table maybe sunk down, those are called the transition metals. They're the transition between this part and that part. We have vertical columns and horizontal rows. The columns are called families or groups. And we find that within a family or a group, because Mendeleev set the table up this way, is that there are common properties among those elements. The horizontal rows are called periods. The main group elements are labeled with a number and the letter A, or they're also numbered just 1, 2, and 3 through 18. There's 2 systems of numbering for the periodic table. There's one that the International Union of Pure and Applied Chemistry recommends, and that's just 1 through 18. And then there's the one that's the current U.S. usage. And since we're currently in the U.S., I prefer that one. That's the one with the A's and the B's. I think it's more informative, at least in general chemistry, it's much more useful. And you'll see on this periodic table on the wall that both sets of numbers are there. In the periodic table I give you for exams, both sets of numbers will be there. I will generally use the ones with the A's and the B's. Transition elements have the letter B, and I already mentioned that. Some of these families have names, and you need to know the names of them. So the group 8A elements are called the noble gases. They're noble. They don't react with other things. Some of these gases have, we are not aware of any compounds that they form with anything. And originally, none of them were thought to make compounds at all. Now we know that a few of them make a couple of compounds. Helium's probably the most familiar. We put it in balloons, and it makes the balloon float. And then if you breathe it in, it makes your voice all high and squeaky. The alkali metals are group 1A. These are very reactive metals. If you take a marble-sized piece of sodium and drop it into water, it will explode. You can look up YouTube videos of people putting sodium in their swimming pools. I personally would not try that at home, but good luck getting a hold of a chunk of sodium. Anyway, but all of these elements are very reactive. Their names are the alkali metals. I think of them just like, I have 6 children, and they share some very similar characteristics. They're all part of the same family. They're not exactly the same as each other, but they have a lot of things in common. The group 2A elements are called the alkaline earth metals. Fairly reactive, but not as much as the alkali metals. Group 7A, these are the halogens. Those are very reactive nonmetals. Chlorine, bromine, iodine, fluorine. Some of them are gases. One's a liquid at room temperature, and some are solids. So we've talked about this a little bit. Metals tend to lose electrons. The main group metals are more predictable in this. They will form a cation with the same number of electrons as the nearest noble gas. And what that ends up meaning is that the charge on the ion will equal the group number. So metals in group 1 will form +1 ions. Metals in group 2 will form +2 ions. Let's look at how the same number of electrons as the nearest noble gas works out. Let's look at sodium. How many protons does sodium have? 11, because it's 11, it's number 11 on the periodic table. How many electrons does sodium have? 11. So it's got 11 protons and 11 electrons. What's the noble gas that's the closest to sodium? Neon. Neon's number 10. Neon has 10 protons and 10 electrons. So what sodium will do is it'll lose 1 electron, and then it'll have the same number of electrons as neon. So it'll go to 10 electrons. And when that happens, now the overall charge is +1. And so we call this Na+. This is +1 charge. The exponent here is treated a little differently than we treat exponents in math. And I think the purpose of it is to avoid confusing these things for exponents. We don't want someone to think that we're taking some variable Na and raising it to the +1 power, because that's not what we're doing. So we write the charge symbol, plus or minus, and if it's 1, we don't write the 1. That's kind of a theme. Chemists seem to not like writing the number 1. We avoid it. So that would be Na+. We'll understand why they do this later. For now, we're just going to be able to predict what. The nonmetals tend to gain electrons. So let's look at fluorine. How many protons does fluorine have? 9. How many electrons? 9. So fluorine is going to gain an electron to have the same number of electrons as neon. So when it has 10 electrons, then it's going to have a -1 charge. And so we're going to call that F minus. It's a superscript, and we don't write the number 1. Pardon me?
You got toothpaste.
Toothpaste, yes. There's fluoride in your toothpaste. What about oxygen? How many protons does oxygen have? 8. And how many electrons? 8. So what kind of an ion do you think oxygen's going to make? A 2 minus. It's going to gain 2 electrons, and then it's going to become O 2 minus. We write the number before the sign, because if you were doing exponents in math, you'd write -2, right? This is math. This is chemistry. Okay? Any questions? So in general, the alkali metals, group 1, are going to form +1 ions. The alkaline earths are group 2A. They're going to form +2. Halogens, group 7, they're going to form -1 ions. And then the oxygen family, someone really should come up with a name for them. They should form -2. Maybe we could call them the atoms family. I don't know. All these slides just repeat themselves. So the main group elements, cations with predictable charge, the charge equals the group number. One way to think about the nonmetals is the charge is equal to the group number -8. That works for some students. I'll show you a different way also. The transition elements, they're very unpredictable. So we're not going to talk about those yet. So here's the periodic table. Group 1A, all of these elements form +1 ions. Group 2A, +2 ions. Here's aluminum in group 3A, +3 ion. Yes, it's very boring. So somebody yawned loudly. It's okay. I have child-induced attention deficit disorder, and I get distracted. Question?
Isn't there some rules for like zinc and zinc and?
There are rules for zinc and silver, and we'll get to those. For now, we're just going to stay with the predictable people. I tend to personify elements. Okay, let me show you the nonmetals here. So your book says it's the group number -8. So here's group number 5. 5 minus 8 is -3. So if you can remember that, that's great. I think of playing a board game, I guess because I play board games with my children sometimes. And so here, you're going to start here, and you have to figure out how many spaces do I have to go backwards. Well, for nitrogen, you start at the noble gas, you go -1, -2, -3. It has a -3 charge. So sulfur, we're going to start at the noble gas, go -1, -2. Iodine, you start at the noble gas, go -1. All of these guys are -1 charge, -2, -3. Any questions? Predict the charges of the monatomic ions formed by these main group elements. So, nitrogen. It's a nonmetal because it's over here, and so we find it, and we go 0, -1, -2, -3. So if we're going to write that, the symbol for it would be N 3-. How about rubidium? +1. Rubidium is in group 1. It's going to have a +1 charge as an ion. So rubidium, Rb+. Any questions?
When does it start going positive? So like it goes 0, -1.
Good question. When does it start going positive? The nonmetals form negative ions. The metals form positive ions. And so it's at this stair-step line is where it switches. So tin, Sn, is a metal, and so it's going to have a positive charge. The nonmetals, the semi-metals, We're not going to see them really form ions, at least in this class. So they're kind of in a no man's land in between. Non-metal, negative. Metals are positive. Good question. Any other questions?